Hello guys, and welcome back to the PyTorch Basics course. In this video we're going to cover the third type of tensor operations called broadcasting and element-wise operations. First, let's try to define what element-wise mean. Element-wise operations are extremely common operations with tensors in neural network programming. Let's lead this discussion off with a definition of an element-wise operation. An element-wise operation is an operation between two tensors that operates on corresponding elements within the respective tensors. These two elements are said to be corresponding if the two elements occupy the same position within the tensor. The position is determined by the indexes used to locate each element. So the basic idea behind element-wise operation is just an operation that is carried out between corresponding elements within different types of tensors. And when we carry out element-wise operation, the two elements must occupy the same position within the tensor. Suppose we have the following two tensors. First, we define T1, which is a 2x2 tensor, and we define another tensor T2, which is another 2x2 tensor. Both of these tensors are rank 2 tensors with a shape of 2x2. Rank 2 tensors because we have axis 0 and axis 1. This means that we have two axes that both have a length of 2 elements each, one across the row and another one across the column. The elements of the first axis are arrays, and the elements of the second axis are numbers. So when we go across the rows, each element is an array, and when we go across the column, each element is just a number. We can verify this by printing out the first row. T1 0 prints out the first row 1 2, and T1 index 0 and another index 0 prints out the first element 1, which is the first row and the first column. We know that two elements are said to be corresponding if the two elements occupy the same position within the tensor, and the position is determined by the indexes used to locate each element. So two elements occupy the same position if the position determined by the indexes locate each element. So T1 and T2 are two tensors. They're different tensors, and if we use the same indexing to access the elements in the two tensors, we can see that 1 and 9 are the corresponding elements within these two tensors. So when we perform element-wise operations, we always perform it on elements that are found in the corresponding position or in the same position. This allows us to see that the corresponding element for the 1 in T1 is 9 in T2. The correspondence is defined by indexes. This is important because it reveals an important feature of element-wise operations. We can deduce that tensors must have the same number of elements in order to perform an element-wise operation. Since each of the corresponding elements must be in the same location, if we have one element in the first tensor and it doesn't have a corresponding element on the second tensor, that means we're not going to be able to execute element-wise operation. So this leads us to deduce that tensors must have the same number of elements in order to have elements in the corresponding position in all places and perform element-wise operation. We'll go ahead and make this statement more restrictive. Two tensors must have the same shape in order to perform element-wise operations on them. So we have arrived at the conclusion that two tensors must have the same shape in order to carry out element-wise operation on them. Let's look at our first element-wise operation, addition. You might think that addition is just a very basic operation, but don't worry, it will get more interesting as we proceed. So let's add the previously created tensors T1 and T2. So T1 plus T2 will be 10 because when we add the corresponding elements, they always sum up to 10. This allows us to see that addition between tensors is an element-wise operation. Each pair of elements in the corresponding locations are added together to produce a new tensor of the same shape. So always when you add tensors of the same shape, the output will always be, or will always have the same shape as the two tensors. So addition is an element-wise operation, and in fact all the arithmetic operations such as add, subtract, multiply, and divide are also element-wise operations. If addition executes element-wise operation between two matrices, then you can assume that all of the other arithmetic operations also perform element-wise operations between two tensors. Using these symbolic operations, now instead of adding the two tensors, we can add a tensor and a scalar. But what happens when we add a scalar to a tensor that is 2 by 2? It's completely different from the previous case because we only have one element during a scalar and the tensor has a shape of 2 by 2. And we need to create a new concept in order to understand the outputs of these operations. But for now, let's see that these four operations can be used using PyTorch, or instead of using these operations, you can also use the built-in tensor object methods such as add, sub, mul, and divide, or div, in order to perform the same operation. Remember that we use the tensor object T1, then use the add method, and then add the element as a parameter which we want to add to the first tensor. Here we can put a tensor or a scalar as a parameter, and it performs the same operation and gives us the same output. The first solution that may come to mind is that the operation is simply using the single scalar value and operating on each element within the tensor. We might assume that it's just carrying the scalar and then adding it on each element in order to get the output. This logic kind of works, however, it's a bit misleading because under the hood in PyTorch, this is not what is happening. And it breaks down in more general situations where we are not using a scalar. To think about these operations differently, we need to introduce the concept of tensor broadcasting or just broadcasting. So in order to understand the addition operation between a tensor and a scalar, we have to introduce a new concept called broadcasting, and broadcasting describes how tensors with different shapes are treated during element-wise operations. Broadcasting is a concept whose implementation allows us to add scalars to higher dimensional tensors. Let's think about the previous operation, t1 plus 2 operation. Here the scalar valued tensor is being broadcasted to the shape of t1. So instead of our analogy before where we just assumed that we are just adding the scalar to each element, what is happening under the hood in PyTorch is it's broadcasting the scalar first to be the same shape as the first tensor, and then the element-wise operation will be carried out. So not always broadcasting does not always occur when we try to add a scalar with a tensor, but also tensors of different shapes. Here we can see that the first tensor is a shape of 4 by 3, and the second tensor only has 3 elements. So in order to perform addition between these two tensors, first we must broadcast the 3 and replicate it 4 times in the rows so that we could have a shape of 4 by 3. Remember that the element-wise operations always need to be in the same shape so that we can add the corresponding elements. Once that occurs, then when we see the output, it's going to be the addition between the elements in the corresponding positions. We can see what the broadcasted scalar value looks like using the broadcast to numpy function. So when you perform element-wise operations in PyTorch, it usually does the broadcasting operations under the hood, and you don't know what is happening behind the scenes. But if you want to understand what it's doing, it's just using the broadcast to method of numpy to broadcast the scalar into the shape of the tensor. Now you see that the scalar 2 is going to have a shape of 2 by 2, and it's just going to duplicate the value to fill in the remaining positions. This means the scalar value is transformed into a rank 2 tensor, just like T1, and just like that the shapes match, and the element-wise rule of having the same shape is back in play. This piece of code here paints the picture, so to speak. This T1 plus T2, T1 plus 2 is the addition between T1 and the scalar 2, and you can see that under the hood it's performing what it's doing is really like this. So T1 plus torch.tensor np.broadcast to 2 to the shape of T1, and then performs the addition operation. Remember that you don't have to do this by yourself. If you just type 2, it's going to give you the same output. This is given to give the analogy of what is happening behind the scenes when PyTorch is adding a scalar with a tensor. At this point, you may be thinking that this seems convoluted. So let's take a look at a trickier example to hit this point home. Suppose we have the following 2 tensors. So the first tensor is going to be 2 by 2, and the second tensor is going to be a 1 by 2. Or since we just have a single array, the shape of the second one is just 2. What will be the result of this element-wise addition operation? Is it even possible given the same shape rule for element-wise operations? So this is not a scalar, so the first thing that we need to do is to convert the second tensor into the shape of 2 by 2, and then we can perform the addition operation between the 2 tensors. Even though these two tensors have different shapes, the element-wise operation is possible, and broadcasting is what makes the operation possible. The lower rank tensor 2 will be transformed via broadcasting to match the shape of the higher rank tensor T1, and element-wise operation will be performed as usual. So we're going to broadcast T2. So T2 is a tensor, so now we're just converting it back into a NumPy array in order to use the NumPy function. And we use the broadcast2 method to broadcast the second tensor into the shape of T1. So we use T1.shape as the second parameter for the broadcast2 method. Then we see that 2, 4, the first one-dimensional array is now transformed into a 2x2 tensor, or NumPy array in this case. And now we can just add the two tensors in this way. The concept of broadcasting is the key to understanding how this operation will be carried out. As before, we can check the broadcast transformation using the broadcast2 NumPy function. After broadcasting, the addition operation between these two tensors is a regular element-wise operation between tensors of the same shape. So once it is transformed into the same shape as the first tensor, then we can carry out the element-wise operation. Remember that it's not only arithmetic operations which are element-wise, but also comparison operations are element-wise. Comparison operations are also element-wise operations. For a given comparison operation between two tensors, a new tensor of the same shape is returned with each element containing either a bool value of true or false. And there is a behavior change in PyTorch version 1.2.0. Comparison operations return data type has changed from integer to Boolean. So let's see an example to understand what this is saying. So before, in previous versions of PyTorch, when you try to compare two tensors using a comparison operator, the output is going to perform element-wise comparison between the corresponding elements. And if it is true, it's going to return an integer 1. And if it is false, then it's going to return an integer 0. So in this case, 1 is less than 3, it's true, so we have 1. And for the rest of the elements, 2 is not less than 1, so it's false. So we have 0. But starting from version 1.2, instead of returning an integer, it's returning a Boolean value. So we get true, false, and false instead of 1, 0, and 0. This is a minor detail that we must remember, because when we perform these types of operations, we need to understand what the data type of the returned tensor. Now let's see element-wise comparison operation examples. Suppose we have the following 3x3 tensor. Let's check out some of these comparison operations. So instead of using the less than, greater than, and equal to sign, we can use the built-in PyTorch methods, such as EQ for equals, GE for greater or equals, GT for greater than, LT for less than, and LE for less than or equal to. So we're going to compare the tensor with the scalar 0. Remember that since we are making comparison operations between a 3x3 tensor and a scalar, it's going to perform broadcasting first on the scalar, just like the arithmetic operations. and it's going to compare 0 with each of the elements in the first tensor, and if they're equal it's going to return true, and if they're not equal it's going to return false. The same thing applies for the other operations. Thinking about these operations from a broadcasting perspective, we can see that the last one, less than or equals 7, is really like this. So just as before, we can use the less than or equals sign to do the same kind of operation as LE. Then we can broadcast the scalar into the shape of the first tensor first, and then convert this back to a tensor because this is a NumPy array. Then it's going to compare the tensor t with the broadcasted scalar 7, and then we can get the same output. Or instead of using the np.broadcast2 method, we can just create the tensor like this with a shape of 3 by 3 as tensor t, and then we can do the comparison operation. These two are the same. Now we have finished understanding the comparison operators. Next is element-wise operations using functions. With element-wise operations that are functions, it is fine to assume that the function is applied to each element of the tensor. So there are a lot of functions, built-in functions in PyTorch that we can use, such as the absolute value, square root, negative, and taking the negative and then the absolute value. So when we perform these functions, they're also element-wise operations because they're being carried out on each element of the tensor. So the absolute value just takes the absolute value of each element in this tensor, and the square root takes the square root of each element. That's why they're called element-wise operations using functions. Next are in-place operations. In-place operations are similar to the built-in methods, but the only difference is that they add an underscore with besides the built-in methods. So an in-place operation is an operation that changes directly the content of a given tensor without making a copy. So when you're trying to add the tensors using the built-in functions, it's basically creating another copy in order to store the output between these two operations. But when you add an underscore, this is saying that instead of creating a copy in order to put the output, it's going to add the second tensor on the first tensor in place without creating another copy. So if you try to output T1 again, now T1 will be gone because it changes directly the content of the given tensor in place. So T1 will be replaced by the new output. But in this case, T1 will be preserved because we add T2 into T1 and create another copy to save the output. In-place operations in PyTorch are always postfixed with an underscore, such as the add and scatter methods. Python operations like plus or equals or multiplied by or equals are also in-place operations. So when you perform these types of operations, instead of using the underscore value, remember that they're also doing the same thing. Sometimes you might have a variable plus or equals something, a number or another tensor. So this is basically replacing the elements of the first tensor by the output of this operation. Okay, the subtraction and multiplication operations are also the same, and all of the operations that we have mentioned before, if you just put an underscore on each of the built-in methods, remember that it's going to be an in-place operation, and the first tensor will not be preserved and a copy will not be kept. That's all for the explanation about the broadcasting and element-wise operations. Next, we're going to implement them by using Jupyter Notebook. Okay, last time we stopped on broadcasting operations. So broadcasting is a concept whose implementation allows us to add scalars to higher dimensional tensors, and the lower dimensional tensor will be broadcasted to the higher dimensional one so that they have the same shape. So now let's implement this by using the two tensors, which are a 2x2 tensors. First, we need to import Torch. Next, we're going to add the scalar 2 to the first tensor, and remember that since we are adding a 2x2 tensor to a scalar, this requires broadcasting. Now you can see that we are adding 2 to each of the elements of T1, and we get the outputs 3, 4, 5, and 6. Next, we're going to see how the broadcasting is being implemented behind the scenes by using the np.broadcast2 method. So we're going to broadcast 2 into the shape of T1. Here, np is not defined, so we need to import numpy as np first. Now you can see that the scalar 2 has been broadcasted into a 2x2 numpy array. Remember that this is not a tensor. If it is an array, it means that it's a numpy array and not a tensor. And if you want to add this broadcasted scalar to the previous tensor, you need to convert it into a tensor first and perform the element-wise addition. Now you see that the output is the same as before. Next, we're going to create another tensor T3, and it's going to have a shape of 2 because it has 2 elements. Now let's check the shape of T1. We can see that it has a shape of 2x2, and the tensor T3 has a shape of 2. When we add the tensor T1 and T3, we can see that even though the second tensor has a shape of 2 and the first tensor has a shape of 2x2, it has gone and already performed the element-wise operation between the two tensors. But in order to see what is happening behind the scenes, we can execute this code by using the np.broadcast2 method. Now you see that the third tensor has been broadcasted into a 2x2 tensor by replicating the tensor 2 times, and then it basically added the corresponding elements of T3 with T1. Next is Elementwise comparison operation. For this purpose, we're going to create another tensor T. Note that the equal, if you use a single equal to sign, then it means it is an assignment operator. But in order to perform the equal to comparison operation, you have to use a double equal sign, or you can use the built-in PyTorch method EQ and then pass the second number as an argument. Here, note that even though 0 is a scalar and t is a 3x3 tensor, it's going to broadcast 0 into a 3x3 tensor first and perform the element-wise comparison operation. Now it's basically comparing 0 with each element and telling us whether it's true or false. We can also perform other kinds of comparison operations, such as greater or equals, greater than, less than, and less than or equal to. Next are the built-in element-wise operations using functions. These are separate functions, built-in functions used by PyTorch that are performed element-wise, such as the absolute value, and we're going to perform them on this tensor. This is basically taking the absolute value of each element in the tensor, and this one is taking the square root, the negative, and taking the absolute value of the negative. Last but not least, we're gonna see in place operations. For this purpose, we're gonna create two tensors with just one element. First, we're going to see the difference between the built-in addition operation and the in-place addition operation. The only difference is just adding the underscore. Here, the .item method is just extracting the element inside the tensor. Remember that every time that we output a tensor, it gives us the tensor function. This means that this is not an array, or this is a tensor object, but if you use the .item method, it's going to just display the element within the tensor object. So since we want to see the number 2 and not the tensor object 2, we can use the item method. Here you see that we do not have the tensor function, we only have the element 2 because we called the .item method. The normal addition is basically adding b into a, and this is also doing the same thing and adding b into a. Now you see that when we perform this operation and output a is kept the same because it created a copy of a and stored the output. So if you want to see the output of this operation, you have to assign it into another variable and then output that variable. But in case of an in-place operation, a will be changed from 2 into the new output. Now it's adding the value 6 into 2 and it's 8, and you no longer have a as 2 but as 8. in-place operations might be handy when we perform certain kinds of operations, which we will take a look at in a later video. We can also do the same thing with the rest of the operations, such as subtraction, and in-place subtraction. And this is for multiplication. We have performed the in-place operation using just a single element. Now we can perform this by using an array or a one-dimensional tensor. Note that here I'm not using the dot item method. That's why we have the tensor object here. And when we add the two tensors here, here we have a as the addition between these two, but it's going to perform the in-place addition for the second case. Remember that this one, 12, is just the first one, and here we have the second one added to the first one. And another one is a multiplication operation, and the difference between the normal and the in-place multiplication. That's all for this video.
Audio Jungle.